Okay, so we need to sketch this. Let me say something about functions with fractional exponents. So what is the domain of this function, first of all? That's actually very important. Is there any value of x that you cannot put in here? It's actually everything, okay? The problem with fractional exponent expressions, functions that contain fractional exponents, is that when you differentiate it, what's going to happen to the top? What's going to happen to the exponent? They're going to become, or they can become negative, right? So the domain, you have to be careful here. The domain of the first derivative function will not equal to the domain of the function itself. Okay, so some drastic things might happen. So questions like this, you can get like cusps, right? Because that means somewhere the derivative does not exist. Remember, the derivative does not exist? What does that mean? Derivative does not exist. It means either it's doing this, like sharp turn in and comes out, or it's doing this, like sharp turn in, out. Right? So these are called cusps. So, okay, so these are the things you have to watch out for when you have a fraction exponent. Let's start the same. Step 1. Okay, we got to do the first derivative analysis. First of all, end behavior. As x approaches to infinity, what happens? Y is approaching, right? This is positive always. Also, this is actually going to be really negative, right? Because you put a really large number in there, so it's going to be approach minus infinity. X is approaching minus infinity, that's always positive. This is going to turn into positive, right? Because it's 6 minus of a really negative number. Okay, and the second step is the X-Intercept, right? You know, finding X-Intercept, Y-Intercept, doesn't matter which one you do first. So X-Intercept is 0 and 6. That's nice because it's in a factor form. And C, Y-Intercept is also 0. So it also passed through the origin. Okay, so here comes some, for the second step we got to do some algebra. Okay, and you got to do it very carefully. Product rule, right? So 2 over 3 x to the power of negative 1 over 3. And then plus x to the power of 2 over 3. 1 over 3, 6 minus x, negative 2 over 3. Chained by negative 1 because that's the derivative of 6 minus x. Okay, and you have to know how to factor. Okay, the fastest way is to know how to factor fractional exponents. So first of all, I'm going to factor out 1 over 3. Base x. There's one here and there's one here. The smaller exponent is negative 1 over 3. I'm going to factor out negative 1 over 3. And then for 6 minus x, the smaller exponent is negative 2 over 3. So I'm going to factor out negative 2 over 3. So everything needs to be multiplied by 3 first. So we get 2. And here you get just negative 1. And x, this is gone. Factored out. The 6 minus x, 1 over 3, you have to add 2 over 3. So it becomes 1. Here, you have to add 1 over 3 here. So you get x. Okay, and that's it. Okay, so let's clean that up. The negative exponents go to the bottom. The top you have 12 minus 2x minus x, that's minus 3x. So you can divide the top and bottom by 3, okay, or minus 3, and you get this. Minus of x minus 4, x to the power 1 over 3, and 6 minus x to the power of 2 over 3. Okay, critical numbers. Critical numbers is when this is equal to 0 or undefined. So it's 4, 0, or 6. Let me make the table for the first derivative. so 0, 4, 6, right? Okay, so we have a division. This one here, the 6 minus x to the power of 2 over 3, this is the only one that's going to be always positive. Okay, listen carefully here, please. This is always going to be positive, right? These two, they have the same sign as x and x minus 4. So overall, the sign will be determined by this x minus 4. It's going to have the same sign as this expression, right? Which is a parabola that's going downwards, right? So 0 and 4. So before 0, it's negative. So actually, it's undefined. 0 undefined. Okay, and then from 0 to 4, it's positive, and then it's negative. Okay. Again, you got to do this graphical analysis so that you don't need to plug in numbers. So much faster. This whole process is so long to begin with. So if you're sitting there punching in numbers, oh, is it positive there? Is it negative there? Is it positive there? Is it negative there? It takes so long. So let me explain this one more time. You agree, first of all, if the sign of division, okay, and the sign of multiplication will be the same. The value is different, but the sign is same. So first of all, then I can say, well, the sign, I just want to know the sign. The sign of that is the same thing as this. Right? You have to agree with that. Now, because this one is squared, this thing is always positive or 0. Okay? So then the sign of the whole thing being positive or negative will purely be determined by this part. Okay, so again, just the sign is equivalent to this one. Now x to the power 1 over 3 has the same sign as just x. If x is positive, this is positive. If x is negative, that's negative. So that's why I just analyzed this, and I was able to tell what sign belongs where. So I'm going to change it into product first to do the second derivative. I'm going to keep the negative outside. Differentiate this. It's 1. Differentiate the second one. You get this. Okay, so that's it. Now we gotta find a way to factor, okay? Okay, constant fraction wise, it's 1 over 3 again. Okay, because it's so big, I'm gonna multiply everything by 3 first. Okay, we need to factor out x now, and it's this. That's the lowest power. Okay, what about 6 minus x? It's in each term, and that's the lowest power. So we gotta add 4 over 3 to every x power. So you get 3x. That's just gone. And here we have 2x. Okay, so what about 6 minus x? You got to add 5 over 3. If you add 5 over 3 to that, you get 1. Five over 3, 6 minus x. And if you add 5 over 3 there, it's gone. Okay, so to bring the negative exponent to the bottom, the top expand. I forgot x minus 4 here. So you get 2x squared and minus 8x. Okay, so that and these two cancel out. Okay, so these two add up to plus 8, cancels out with minus 8. And then the 24 will reduce with 3 to give you 8. Yeah, so I think I forgot to change the minus to positive, and I changed it. So the potential inflection points are 0 and 6. So here's the basic table. I'm going to fill in the signs now. The first derivative was equal to 0 all three cases. The second derivative was equal to 0 at 0 and 6. Okay, 0 and 6. Oh, sorry, it's undefined, right? Some part is
0 and 6.
0 and 6 is undefined. Okay, and everything is undefined here. Undefined. Okay, so we already figured out the sign for the first derivative right here. It's negative and then plus from 0 to 4. Everything is negative. The second derivative, if you look, this is always positive, right? X to the power of 4 over 3 because it's even power. So it's just gonna, the sign's gonna matter whether we're to the left or right of the 6 minus x. So let's actually multiply this negative 1 inside. Okay, and we actually get this 8 over x to the power of 4 over 3 and x minus 6 to the power of 5 over 3. And this tells me to the left of 6 it's negative and to the right is positive. Let's draw the curve now. It's going down, it's curving down. It's going up, but it's still curving down. So look, this is that's going to be, okay, we call that a cusp. And then this is going down, down, so this is going to be a maximum, local maximum. And it's going down and up, so it's an inflection point. Okay, inflection point is a max, local max. So can someone actually plug in 4 for me into the original function? Tell me what that is. 3.17 approximately. This is more than enough now to finish the question off. Okay, so we know that at 0 it's going to do this, like a cusp, right? It's going to go around, and that's going to be 6. It's going to go straight down, so it's like undefined, right? Really, really going straight down. And then there's going to be an inflection point there, like this. And this is going to be at 4, it's going to be 3.17. Okay, and this is not going to curve down again. It's going to continue to increase. Okay. That's the picture.